Now we move on to the Young Investigator Award. I'll briefly introduce the award before introducing the speaker. Now, as you know, this meeting is very special, not just because we talk about the wonderful data that we've got with all these wonderful methods and we get to meet each other digitally, but also because of the initiative, which I really support, of supporting early and mid-career researchers. This is always very important in any field of neuroscience or academia or anything, to support people at the early stages, because otherwise you don't get people in the later stages. But there is a particular reason for doing it with these techniques. The machines that we use are often quite expensive, and that can be a real obstacle for people to get into the field. They're not really cheap, like a computer or even a very good computer, but they're not so expensive like an MRI scanner or an MEG scanner, where you're not expected to find the funding for that within your own group. And that can present a real challenge, meaning we get fewer people doing it, meaning we get less diversity, meaning we find out less. But there's also a further problem in that much of the work that we do, you have to get a particular kind of effect for it to be publishable. If we're using interference techniques, and this holds just the same for patient lesion studies or optogenetics or all sorts of other studies, if what you have to do has to get its effect and you don't get it to work, then it can be very difficult to get the recognition that you need from all that work for your career. Part of that is because of the system that we have at the moment, and part of that is because of the nature of using an interference technique. Now, as it happens, the speaker we'll have shortly is a great example of someone who's been challenging both those aspects of the difficulties of using causal techniques. Now, the Young Investigator Award has the goal of recognizing, rewarding, promoting early career academics doing the very best neuroscience research, with a cash prize and a speaker slot here, and further opportunities for ongoing research. And so it's a very great pleasure to be able to introduce today's winner, today's speaker, Daniel Corp, presenting his work on lesion network mapping and on big TMS data collaboration. Daniel is a lecturer in psychology in Deakin in Australia. I personally have been following your work recently, and it's a really great pleasure to have you here. Congratulations on winning the Young Investigator Award, Daniel, and we're looking forward to your talk.
Yeah, thank you very much, Paul. Thank you to the committee as well, and it's a really huge honour. Exactly as you said, I think Brainbox is doing an absolutely magnificent job of representing young investigators like me. I'm getting a little bit older, but no, like you said, it is difficult to sort of make your way, and especially early on in your PhD and just out. And I think this is a really great little community that we've got here, and very proud to be a part of it now. So thank you very much. So I guess I'll share my screen and get on with the talk and present some of my work that comprised the application. Okay. So is that good? Everyone can see that and hear me? That was a yes. Sorry, guys.
Yeah, that's great.
Yeah, perfect. All right. So my work and my application was in the localization and stimulation of brain networks in neurological disorders. So I'll explain all of that in due course. A little bit about my background and how I got into trying to attack these sorts of problems. As Paul mentioned, I'm in Australia and completed my PhD here in 2016, and really focused on TMS, sort of repetitive methods, and also single and paired pulse as well. And from that, I guess, came out with a goal of, translational brain stimulation, but I think came out with a problem of, we've had, as of, a few years ago, one real success story in TMS and that's in depression. Obviously, there are some other breakthroughs that have come since then, but I think the way that we try and identify these TMS treatment targets is largely based on trial and error. We don't really have good, replicable techniques to localize areas of the brain to stimulate in these neurological disorders. And so this led really nicely into a postdoc that I did with Mike Fox and Alvaro Pasqualeone, because Mike Fox is really well established and well known in the imaging circles, and for being quite a creative thinker and coming up with these network localization sorts of methods. And Alvaro Pasqualeone, of course, with the TMS sides of things. So it was really nice to try and integrate these two modalities to come up with solutions. So what I've been trying to work on for the past few years is to use these network localization methods through network mapping, and also then translate that into actually going after these treatment targets that we find with network localization. At the same time, in parallel, I guess, we all know one of the biggest problems plaguing our field at the moment, is variability in response to TMS. So we've been trying to optimize these methods through the creation of big data, which I'll speak a little bit about at the end as well. First off, with localization, what we're trying to do here is use these novel imaging methods to localize treatment targets. So these include lesion network mapping, coordinate network mapping, and these were some of the techniques that I learned in my postdoc. So the main thing that I've done this in so far is a movement disorder called cervical dystonia, but we're also doing a lot of work in other disorders, which will hopefully come out very soon. So I'll talk mainly about the work in cervical dystonia that I've done in localizing. Now, if you don't know much about cervical dystonia, it's a movement disorder involving muscle contractions of the neck, so cervical, and patients sort of, can't control these persistent muscle movements of their neck. It was a really good target for lesion network mapping because there are a lot of different parts of the brain that are implicated in this disorder and dystonia in general. I mean, you'll read one paper and it will be, the cerebellum is causally involved in dystonia, and then you'll read another and it's, traditionally the basal ganglia, and another they'll say, oh, we found abnormalities in the frontal cortex and the visual cortex, and you sort of throw your hands in the air. So we had a really good target with cervical dystonia here. Now, traditional lesion mapping, which I'm sure we all know from, I guess, Year 12 psychology, is where we get a lesion and then simply look at where that lesion occurs. And we say, all right, fantastic, Broca's area, consistently lesions occur in that particular area, and that maps really nicely to a loss of function. So really nice for the neuroscience field for hundreds of years, I guess, in trying to map these brain regions to their functions. The problem with that, though, is that it only works where these lesions occur in these focal parts of the brain. So if you've got an example like with cervical dystonia and many other disorders where these lesions occur in really variable regions of the brain, then simply overlapping the lesion location is not going to do much to localize the causal substrate of the disorder. So this is the problem that we were faced with here. So lesion network mapping, what we do to try and resolve this is not just look at the lesion location, but we then map the functional connectivity of the lesions. So we're no longer looking at just the focal location, but we're looking at all of the parts of the brain, or the parts of the brain that are most connected to each of the lesion locations. So we do this using resting state fMRI, and we do this in a large data set of 1,000 healthy scans. This is a really nice resource to have that came out in about 2013, because if you know much about resting state fMRI, it sort of, with such a large data set, provides a wiring diagram for the brain. You can sort of say, all right, let me put an ROI in wherever I like, and then I can get a map of the brain areas most connected to that specific ROI. So that's what we've done with lesion locations here with cervical dystonia. So this concept of mapping not only to the lesion location, but mapping to the parts of the brain that are most connected, is based on this really old concept of diaskesis, that says that symptoms can emerge not only from damage to the focal site itself, but also from disruption to connected brain areas. So based on this concept, and based on lesion network mapping, we're now asking not just in relation to the lesion location itself, but we're saying, are there any specific regions in the brain that are commonly connected to all of these lesion locations? So the big reveal here is that we did find a couple of these spots that were specifically connected to all of the lesions causing cervical dystonia, and they were in the cerebellum and sensory cortex. So we sort of say, it's part of a network, it's part of a broader network that encompasses all of these lesion locations, but there are also these hubs, I guess you can call it, in the cerebellum and the sensory cortex. And, if you mess with the pathway to these hubs, then, in some cases you get these cervical dystonia symptoms. So we validated these findings as well, because just doing lesion network mapping, the work really comes from that large normative data set and from case reports where you pull the lesions. So we thought it was really important to actually validate the abnormality of these brain regions in real patients. So that's what we went and did. So we grabbed some resting state fMRI data, and lo and behold, both of these focal brain regions were abnormal compared to healthy controls. So then we've localized, and the next part of that model that I mentioned on the first slide is we then want to try and stimulate to translate these findings to see if there's actually a clinical benefit. So we've created a little clinical trial here, and got ethics approval, and we're ready to go and everything like that. And unfortunately then COVID struck, and Melbourne's been pretty well locked down over the past 18 months or so. So that's been on hold, but hopefully we can get that started soon. But my collaborator, Juho Jutsa, a little bit more optimistic. The news in Finland is that they have tested 12 people already. They're looking at it from a different approach. He's a PET guy, so he's looking at the network effects of stimulation to that specific site that we found in lesion network mapping. Okay. So this pipeline, this localization to stimulation pipeline that I'm talking about at the start, we're sort of part way through that process in cervical dystonia. And we've started that with a lot of other neurological disorders as well, including essential tremor and Tourette syndrome. So a couple of students have been working on that, and these networks look really, really great as well that they've localized, because they tend to match regions that are previously implicated in disorders. And in fact, if you saw that paper that came out in 2021 that applied TACS to the cerebellum in essential tremor, we're sort of converging on that region as well. So obviously a lot of great evidence of the cerebellum being abnormal in essential tremor. So very encouraging that they actually do localize to these regions. So the next thing that I'll talk about is the optimization of TMS. So I mentioned that we've been doing this in parallel with this localization and stimulation pipeline. But I guess, you know, thinking about one of the main problems that we all know about, and that's variability in response and inter-individual variability. So, you know, we're trying, I guess, to address the problem of small sample sizes here and, you know, continually bringing out papers that sort of, you know, have 14 or 15 people, as we all do, and certainly nothing wrong with that. But we thought that if we can get the field together and create a platform for data sharing, then we can definitely answer some questions. You know, the questions have probably already been answered. It's just that we haven't collated the data yet and analyzed that. So that was our goal in creating this collaboration. It's been really successful so far. It's been a lot of work over the past 3 years or so, but thankfully just published a couple of papers in 2020 and 2021, which was, as we all know, getting some reward for all of your work, which you probably never think is coming when you're in the middle of it, is quite satisfying. So that was good to do this year and last year. So I'm conscious of time, but I'll briefly go through the results here from these analyses. The first paper we did was looking at theta burst stimulation variability. So we obtained 22 studies, had those the results sent to us by corresponding authors, and pulled together the largest data set of theta burst stimulation known yet, or that I know anyway. What we found was really, I guess, agreeing with what we've seen so far with theta burst stimulation, is that tend to see quite high inter-individual variability. So you do, which, you know, is encouraging, see some reliability or reproducibility within individuals. But then when you look at person to person, there's really quite a lot of inter-individual variability there. So another thing that we could really quickly look at was just looking at these distributions, because there have been these a couple of suggestions of these responders and non-responders to theta burst stimulation, but we didn't see that. We saw a pretty normal distribution there. So overall, which was really nice, and I'm sure we're all very happy with this, we saw the expected facilitation and CTBS reduction in MEP responses, which you know, is quite encouraging. And we, in trying to localize a couple of the key sources of variability between individuals, we saw that some interesting sort of nonlinear patterns here with age and ITBS, and also with your baseline MEP amplitude when you're looking at, or when you're expressing ITBS as a percentage of your pre-MEP value. Target muscle and pulse waveform as well were some source of variability there as well. The second paper that we looked at was looking at single and paired pulse TMS data. So here we got 35 studies shared with us from 687 healthy people. And again, more or less agreeing with what's been shown previously, single and paired pulse data, a lot of variability between individuals. But yeah, and again, what's been shown previously is that the motor thresholds are a lot more reliable than these single and paired pulse measures. So there is a lot of data. So I definitely encourage you to go and have a look at the study, and I'll give it a bit of a plug here, and obviously you can cite it profusely if you so wish. But just really quickly, I'll point out a couple of interesting findings. So the first one here, looking at these graphs down the bottom, we saw some nonlinear relationships between motor threshold and age. And quite interestingly, these look to differ between biphasic and monophasic pulses. So I guess if you want to dig back through the literature for Vincenzo Di Lazzaro's work with monophasic and biphasic, and eye waves and these sorts of things. That's really what we had to do in trying to make sense of these findings. But I think, that's really interesting to show that corticospinal excitability is not uniform over the lifespan, and with some more work and some more data, we could really try to bear out these relationships a little bit better. Also, with intracortical facilitation, there's this strong relationship with all of the motor thresholds, actually. And I guess we just thought that if someone's got a higher motor threshold, then it makes sense because the conditioning stimulus is therefore given at a higher percentage of the machine output. So it makes sense that you get this increased intracortical facilitation. And that relationship was also there, but in the opposite direction for Siki as well. And again, we saw this sort of negative relationship with baseline MEP amplitude when expressing all of these measures as a percentage of your initial baseline response. So we're trying to expand this big TMS data collaboration. The response has been really great, and obviously in people sharing their data as well. It's I'm certainly, and we are certainly really grateful for everyone who shared their data. So we're definitely trying to expand this at the moment, and make this, I guess, a data sharing platform, and for it to serve the brain stimulation community. Hoping for this to be able to answer questions, these sort of big questions about neurological health that we just can't seem to do with these small sample size studies. And ultimately, as per my goal with the localization and stimulation, is to also use this to optimize TMS as a therapeutic tool to help these folks with these neurological disorders. So thank you very much. Again, a huge honor to win this award, and thank you very much to the committee and the organisers.
Brilliant. Thank you, Daniel, for all of that. That was fantastic. Thanks for showing us a bit at the beginning about your own trajectory through this, and then great to see the lesion network mapping stuff, and then the open, wonderful initiative you've taken there, leading this, or can make a real contribution to the field and to several fields, I think, and I hope in the future. So that's great. I was wondering, and I'm aware this is the middle of the night for you in Melbourne time. So I'm wondering if I could.
Not too bad. It's only 11:30, so it's okay.
Only, okay, well, that's obviously a time we're all preparing our talks for the following morning normally. I was just wondering, from your sort of personal perspective, getting this big collaboration going, you just sort of showed us this huge amount of data. I'm interested in what it's like from a personal perspective. What are the challenges that you found in trying to get a kind of a coordination there? And what was the hardest bits? Was it working out what paradigm to go for, or were there other challenges?
I think actually getting the data was less hassle than I thought. People were really generous, and it was, with TMS data, it's easy to de-identify and share across. It would be a whole lot more complicated if we're talking imaging data, I think, which we're trying to do to sort of make our lives even more difficult. But I think the analysis of it, I probably, when I first went into this, naively just thought, we'll just put it in a big pot and stir it up and see how you go, and run a couple of linear regression models and see what the results are. But it definitely took some upskilling, and learning some of these more complex statistical sort of models that we had to use to actually do this properly. And thank God we did, because those initial sort of prelim results certainly look a lot different when you do things properly statistically. So that took me a while to get my head around and actually implement, and then I guess just handling the amount of data was the most time consuming thing. But like I say, people have been really generous. So that was actually the easy part.
That's really interesting. I hadn't initially thought of the problem of all this complicated statistics you'd have to do there. Yes. We have a question from Helen Nuttall. Would you like to unmute yourself, Helen?
Yeah, sure. Thank you very much for that lovely talk, and congratulations again on the award. Really nice presentation. My question was, I wondered if you could say a bit more, please, about what you think is happening with the non-linear association between motor threshold and age that you mentioned.
Yeah, I think I could probably share my screen and go back to that slide. Yeah, so I think what's happening, I guess, when you're looking at the early part of the x-axis here, you're looking at sort of lower corticospinal excitability for younger people. Unfortunately, we didn't have a lot more data from teenagers and children on this, but in all of the graphs, it does look as though you've got this uptick in, decrease, I guess. It actually is in corticospinal excitability for these younger people. And then I guess that sort of flattens out as people, people's brains develop and get into middle age. And then the interesting thing was with older adults, it seemed to either drop off, meaning that there was this decrease in, oh no, that would be an increase. Yes, that would be an increase in corticospinal excitability. But yeah, what I found interesting and what I referenced before was it sort of seems to be a little bit different with the biphasic pulses. So explaining that, I think it's just a matter of what aspects of the neuron that the biphasic pulse is hitting as opposed to the monophasic pulse. So I guess, if you're thinking about the eye waves and these sorts of things, they're sort of, I don't think it's completely established. Trying to wade through De Lazzaro's papers from sort of, 2002, but, perhaps hitting earlier eye waves with these biphasic pulses, and definitely just a different aspect of the corticospinal cells that are being actually activated with these biphasic pulses.
Thank you. Really interesting observations, and great to see this big data approach as well. Thanks again.
Cheers. Thanks, Al.
Thanks, Daniel. There's a question from the audience from Nivetida. Can you unmute yourself, Nivetida? Otherwise, we'll read it out for you.
So, hi, can you hear me?
Yep.
Yep.
Yeah, great. That's really great work, Daniel. So I have actually two questions. The first one is, do you think there are other factors that you have not been able to examine from this big data set, which you think may contribute to the MEP variability?
Yeah, the one that struck me, I think, is stimulation intensity. So we always use or most of the time we use a 120 of resting motor threshold or a 1 millivolt response. But I think people are realizing that, results can be really variable based on the intensity that you use. So I think that's one of the big things that we've got to try and solve. And people have tried to solve this with doing input-output curves, which are great, but they are really time consuming. And, if you're doing, it's only really plausible, I guess, if you've got a lot of time and you're really probably delving into the methodology of stimulus intensity. But if you're doing, a trial or something like that, where you just want to do some quick measures of corticospinal excitability, it's a little bit more difficult. But yeah, I talk about that in the discussion a little bit, and it was something that I definitely had trouble with myself. But I think creative ways of figuring out stimulation intensity that can be more uniform will definitely lessen that inter-individual variability.
Okay, and the second question is, in your in the 2021 publication, where you've seen the motor threshold to be negatively correlated with the baseline MEP amplitude, could it be that you are observing floor and ceiling effects with the paired pulse results? Say those with lower motor threshold tend to have a larger baseline MEP amplitude, and hence there is less room for facilitation. So you would see less ICF in these individuals. So do you think that it's just the ceiling and floor effects that we are seeing in the data set?
Yeah, I think that does explain some of it. Really interestingly, we saw the same relationships with the theta burst stimulation data. So I guess someone could say, well, don't analyze your data as a percentage of the baseline, but I think it was really important to highlight all of these relationships because that's what nearly everybody does. To answer your question, I think that floor and ceiling effects probably, that's the most logical explanation for it. I think with the theta burst data, we could explain it as a regression to the mean, because you're taking a block of MEPs at the start, and so it's more of a statistical phenomenon. If just by chance your MEPs are higher, just by chance, then there's going to be this regression to the mean or this normalization when you again collect the data after the theta burst. But with the paired pulse stuff, we can't say that as a reason, because of course the single and paired pulses are given at the same time. They're interleaved randomly in there. So that was what I went with. What you said, the floor and ceiling effects, that was the main reason that I went with in the discussion. So to answer your question, yes, I think that makes up most of it.
Okay, thank you.
Great. Again, in the interest of time, unfortunately, we should probably call it there. Thanks again very much, Daniel, for the fascinating talk, and congratulations again on the Young Investigator Award.
Thank you very much. Cheers.
Just wanted to quickly jump in and say thank you or congratulations as well from Brainbox, Daniel, and we'll follow up with you very soon with the physical aspects of the award and make sure you get those, the novelty size check and so on. We'll make sure it gets its way to Australia.
Beautiful. Thanks, Dan. Cheers.
Great. Well, we'll stick to the program, I suggest, and after a short interval, then we'll be resuming with the keynote at 3:10 UK time. See you then.